Assalamu alaikum. My name is Mohammad Anas Ibrahim, and in today's video or class, I will discuss AS topic chemical equilibrium. Equilibrium is term related to the chemical reaction when the reaction in the reversible phase. There are many type of the chemical reaction. Some are called irreversible chemical reaction and some called as a reversible reaction. Just like in a common example, if you take like a many biological process in our body is irreversible as well as some are the reversible. For example, some of the skins, scars, cuts, it's ultimately heal up over the period of time. So it's a biological process which is reversible, and some are irreversible like decay of the permanent teeth, etc. It not become heal up over the period of the time. Similarly, the blockage of the arteries, it maybe undergo the bypass process, but cannot be heal up. So similarly, there are the many different type of the chemical reaction which classify as a reversible reaction and irreversible reaction. First of all, very simple example, if you consider that the salt called copper sulfate, one of the salt which is commonly known and used in the chemistry is called copper sulfate. For example, if you write the formula of the copper sulfate, which is CuSO4, is available in the hydrated form, which means that the sum of the water will be add up to the crystal of the copper sulfate, which is royal blue or blue in color, which is frequently used in the chemistry. But if you go hide this salt, heat it strongly by putting the flame or the temperature, eventually the all water will be lost and it's become totally dehydrated by releasing of the all is water. This is called hydrated salt, which is blue in color. And after that, this become a white or colorless. It's definitely white because it's in a crystal form and the water will be lost. This is a process of heating when the salt is put on the heating and in a Bunsen flame. But if you are trying to do something reverse, means that you purchase some copper sulfate crystal which is already dehydrated form and the drop wise added the few drops, the process becomes reversible and they also produce a copper sulfate which is hydrated in color, which is hydrated salt and blue in color. This is a salt copper sulfate which exists in the hydrated as well as unhydrated form. Hydrated means salt plus water is a part of the composition of salt as well. And the second term is used which is called dehydrated, means the all water will be lost, evaporate and no contain water particles as a composition of the salt. Usually transition metal salt show the variety of the nature, D block element, transition metal salt, variety of the salt which is hydrated. So is one of the example which show the reversible nature of the chemical reaction, means that the reactant converted into product as well, product again reacted back into the reactant side. The one more reaction which is more frequently, more commonly used in the chemistry called Haber process, means this process is a name on the chemist, but the process is called where the nitrogen present in the atmosphere and hydrogen, they combine together, both are in the gaseous form at a certain temperature and pressure, which is mentioned mostly around the 450 temperature and likely to a pressure about the 200 atmospheric pressure. And in the presence of catalyst, this condition have to be remembered because examiner in AS level chemistry assumes to be you should have to learn this standards values. Why this standard would be set, we will discuss definitely later on this video. But for now, right now, you have to be remember, and this one produce NH3 called ammonia gas. So at particular temperature where the condition is supplied temperature, pressure and catalyst, when the nitrogen and hydrogen get enough energy to produce the ammonia, on the simultaneous way when the reaction carried out in this condition, ammonia bond or bond energy will be enough to react back ammonia into the decomposing form of the hydrogen and nitrogen. One more example of the reversible reaction which is very commonly exists in the chemical lab is this one called 2Hi, hydrogen iodide particles. When they are heated in the normal flame, it's generally produce hydrogen and iodine both in a gaseous phase, and this one can also be easily seen by the change in color of the iodine because it is purple in color. There are the few chemical reactions. This was definitely not performing the chemical lab because the temperature and pressure is too much high, and we are generally discussing in the lab. But the other reaction, hydrogen iodide, will be a copper sulfate we generally use in the chemical lab for the demonstrating purpose. One more reaction which is very commonly and frequently used is the nitrogen dioxide gas. When you cool down, the nitrogen dioxide gas readily converted into the dinitrogen tetroxide form, and this balance equation is here too. This color is brown. This gas is brown in color. When you cool down, this color will be disappear, and ultimately you see the test tube will be completely transparent. Nitrogen dioxide is brown in color. When you just put down this test tube, sealed test tube which contain the nitrogen dioxide gas in a cold water, so this nitrogen dioxide converted into the dinitrogen tetroxide N2O4, and once you bring back this test tube with a normal temperature or slightly heated, they again produce a nitrogen dioxide which is brown in color. So very visible change in the color. Can you understand or demonstrate how the reaction is reversible, chemical reaction are reversible? So when we use the term chemical equilibrium, first of all, we must understand that the chemical equilibrium term is only limited with the reversible chemical reaction where the reactant and product both continuously undergo with each other. In simple way, if we define the term reversible reaction, so reversible reaction means reactants react together to form products, as well as product react together to again produce reactant. This is a both way or two side process. We also said reversible reaction means that the reactant converted into product and product also converted back into the reactant. In similar way, we also said that the reaction which never goes to completion, because they never goes to complete because the product is also formed, and when product is formed, the reaction kick back into the reactant. Reaction continues in both direction, reactant to product, product to reactant. They all are correct and used to define the term reversible. Also, till now, I make sure that you can understand the two terms. First is just for the examples, chemical reactions, one or two chemical equation examples for understanding purpose, and how the reversible reaction will be marked. Because of the reversible nature, we generally use double-headed arrow in this form. It's quite okay. If you use in this form, this is also acceptable, and also in this way, both show the same values, both consider almost correct, and nothing to be special about this arrow description right now here. When the chemical reaction becomes reversible, means that the reactant react together to form product, and product particles on the same temperature pressure condition get enough activation energy to react back into the product. So two-way process will be start. One process is the rate or process speed of conversion of reactant towards product, and the second process is reverse. Product also converted back into the reactant. I also already mentioned that the reversible reaction, because of the two side or both side nature, reactant and product both are convergible state. Reactant converted into product, product converted into reactant. This process is in both way, both direction. So when the both reaction is occur, reactant converted into product and product converted into reactant back, there's some speed through which the reactant particles converted into the product, as well as the product particles when approaches to the sufficient level converted into reactant. If we draw the random graph for the understanding purpose, time versus concentration of reactant. So initially reactant quantity will be higher side, and gradually reactant particle react together and converted into the product. So the reactant particle concentration will be decreases. This is a concentration of reactant. For the differentiation for differentiate, there is a zero product at initial time interval, because the reaction is just going to be in start. We, for the simplicity, write double-headed reactions with this one form. So product initially is zero, but after the certain interval of the time, when the product particles appear to be formed, when reactant particles are produce, they are also collide with each other and produce product. When the product is formed, they also, or the sufficient level, it becomes a maximum, because here it means that the reactant particle react at maximum level, or we said that because the reaction is reversible, the reaction reach the equilibrium. So once the time or concentration change becomes flat or parallel to x-axis, this is the time where the equilibrium is reached. Not this one. This is a level where the reactant and product both becomes equal. This is not necessary for the chemical equilibrium. This is the most common mistake among the students considering the equilibrium concept. The equilibrium means that the amount of the reactant and product becomes equal. No, nothing this one. Equilibrium means when the rate of production of reactant towards product side and also product towards reactant side becomes equal. Here, this is a time interval called time required to become equilibrium. It's maybe or maybe not the concentration of reactant or product becomes equal or not. Sometimes it may be or may not be. So doesn't necessary is that the reaction, when the reaction, reversible reaction achieve equilibrium, the concentration of reactant and product becomes equal. It might be or not be. Sometime or some chemical reaction may choose the path where the amount is also become, but the fundamental process is that when the rate of forward reaction becomes to the rate of backward reaction, this this state in the chemistry or chemical equilibrium is in reversible reaction is called chemical equilibrium. When rate of forward reaction, for simplicity we write as this one, rate of forward reaction. Forward reaction generally assumed to be a reactant towards product side. Rate of forward reaction 1 is equals to rate of backward reaction, means product towards reactant side. So when the two rates are equal, this is term is called, or this state of chemical equilibrium. When the chemical reversible reaction achieve this state of chemical reaction, reversible reaction, this state of chemical reaction, chemical reversible reaction is called chemical equilibrium, or sometimes it's just called chemical equilibrium, sometimes it's called chemical dynamic equilibrium, or just equilibrium. So one more term is here. You must have to be remember the definition of chemical equilibrium for AS level or any other board you are trying to attempt for the college grade of first year. So you must have to be remember the term called chemical equilibrium, means that when the rate of forward reaction becomes to the rate of backward reaction. Forward reaction generally supposed towards left to right, which is a more convention way, means reactant towards product side, and backward more convention way is product towards reactant side. Because the reaction is continuous in both way, so that's why we have mentioned that the rate of forward reaction and rate of backward reaction. So hopefully you may understand the term is, which is referred as a chemical equilibrium. Chemical equilibrium means that when the rate of forward reaction and rate of backward reaction becomes equal. This is also known very well familiar that the term chemical equilibrium is has some characteristics, and this definition is also classified as a characteristic of the chemical reaction as well. During the chemical reaction, they are the different. During the chemical reaction, they are the when the reaction becomes to the equilibrium state, we have put the some limitation or condition. First is that when the rate of forward and backward reaction become equal, till rate of forward and backward reaction not equal, we doesn't consider that the chemical reaction or this reversible reaction achieve equilibrium state. The second is the reaction mixture must be closed. If the reaction mixture not be closed, so definitely some gaseous particle will be escaped, and the product is very less or fewer chances to back into the reactant side. For example, we write the equation of the hydrogen iodide in this way. So if we have initially hydrogen iodide, suppose in the liquid form, supposedly, and we heated this one into produce hydrogen iodide in the open container, which is converted into gaseous form. So this all two gases will be skipped. So there is a no chance to get back against to the reactant till the reaction system is not closed. So one condition, which is also definition of reaction, chemical reversible equilibrium or chemical equilibrium, is rate of forward and rate of forward reaction and rate of backward reaction becomes equal. This first point characteristic. And second, must be required a closed system, means no particle will be exchanged in and out from the reaction chamber. Closed system. And reason is that when the system is not close enough, so particle produced in the gaseous form skip and not get enough collision to back into the product again into the reactant side. Third is more interesting fact is that once the equilibrium is maintained, the amount of reactant and become fixed or constant. Amount of reactants or product remain constant, not change. I'm not telling you that they are both equal. Again, I'm showing here. For example, during the chemical reaction, we plot the reactant versus time graph. We measure the concentration of reactant over the period of the time. How we measure the concentration of reactant, this is a separate process we are not going to discuss here. So just we have concentration of reactant decreasing with respect to time. So we plot the curve in this way. And similarly, because initially we don't have any product, so product start from the zero and ultimately reaches the. So here is a time where the reaction mixture becomes time equivalent to equilibrium time. The interesting fact is that when the equilibrium is achieved, neither the amount of the product and reactant will be changed until unless you put the some stress on the chemical equilibrium. Under the certain condition, once the equilibrium is maintained, you don't try to change the equilibrium with any external factors, which is temperature, pressure, and concentration. We discussed definitely. If you are not changing any stress or any condition in chemical equilibrium or chemical reversible reaction, so the time after the equilibrium will be achieved, the amount of the reactant or product does not change, remains same. Here is a for reactant and this one is a for the product. The product and reactant not change, remain on the fixed value here. And also we thought that the rate will becomes constant. There is a no change, no speed change for the conversion. And we also called this one is a state where the reaction achieve the reversible reaction, achieve the chemical equilibrium or dynamic equilibrium. And some student may ask that why we call that dynamic, because equilibrium, this reaction is not to be in a state of the rest. This doesn't mean the reactant particles when converted into product reaction becomes stopped. No, because this reaction is in both way, conversion of reactant towards product as well as a product into the reactant. So reaction continuously happening, continuously form like a seesaw. In both way continuously shuffle across the reactant to product and product to reactant, but with the same speed. This is a very basic definition. I just recall again and again, because a chemical equilibrium, chemical dynamic equilibrium is just understanding that the rate of forward and backward reaction becomes equal. And this is a three specific characteristics where the chemical equilibrium meet or chemical equilibrium required. First is rate of forward and backward reaction equals. Second, closed system is also required. And third is the amount of reactant and product remain constant. Here is a one more graph which also shows a slightly more feature about the chemical equilibrium. For example, initially we have the reactant which is in certain amount, and after the time when the reaction start, reactant particle converted back into the product. So the reactant amount will be decreases after a certain interval of the time. No further change of the reactant particles because the reaction achieved the equilibrium state. Maximum reactant particles back converted into product. And simultaneously on the other way, on the other side, on the other direction is also possible. The product, definitely product particle initially at zero and started to form. But this one also happen commonly in the chemistry. Why this is shows that the reactant and product doesn't intersect each other at all. This curve green is for the concentration of product. But here is a time where the equilibrium is achieved. Time where the equilibrium time is achieved means that you mark the equilibrium time where the graph becomes parallel to the x-axis. Both graphs, reactant to product and product to reactant, both conversion graphs become parallel or horizontal to x-axis. So this is the time where the equilibrium is reached. This means that reactant and product at equilibrium, reactant is and product is in quantity is much less amount of product or concentration of product is much less than reactant as the equilibrium achieved. It doesn't mean that the equilibrium always be in manner that the amount of the reactant is higher or product. Reactant amount and product amount may be equal at equilibrium, may not be equal to each other. Maybe product will be greater at equilibrium and reactant will be lesser. And any case out of three doesn't any contrast with the term called equilibrium. Equilibrium means only the term refer to the rate of reaction where the forward and backward reaction becomes equal, nothing else. I hope I'm repeat multiple times what is mean by the chemical equilibrium is not from associated with the amount, is associated with the speed of reaction. Sometimes you also saw the graph in this way, in which reactant particles in this and products, there is green for the concentration of reactant and this one is a concentration of product. And here is the almost the equilibrium time where T is equals to T equilibrium, x-axis with equilibrium, y-axis with concentration either reactant or product. The green curve is for the reactant and blue curve is for the product. In this case, you saw that the equilibrium time marked with the red, the amount of the product is much higher and amount of the reactant is much lower. It's definitely not equals to zero. The curve is not meet to the x-axis, it's just parallel to the slightly above parallel to the x-axis. So all the way, whether the amount becomes equal, not equal, it doesn't matter. Matter only that the speed of forward and backward reaction becomes equal. Reaction must be closed. And last but not least is that the reaction mixture when achieve equilibrium, the amount of reactant and product remain constant, no further change. There is a three basic fundamental properties which equilibrium contain. Now move further. As we know that the chemical reaction and speed of chemical reaction, first we use the term speed or rate. Rate of chemical reaction may be altered by using the some parameter. For most common example is temperature. If we rise the temperature, the speed of reaction increases. For very common example, not just for the particular chemical reaction, for understanding purpose, we have the cold water and dissolve sugar in it, and we have also some hot water or heating water, and we put some sugar particle on it. We have two different type of water which is very low temperature and put the 1 gram of the sugar here and 1 gram sugar also here. So hot water, the solubility will be increased in the hot water. If you try to dissolve more solute, you generally increase the temperature to dissolve more and more content. Similarly, chemical equilibrium is also affected with the parameters which alter the equilibrium direction. For example, understanding purpose, we maintain the chemical equilibrium, reactant and product speed becomes equal in this. But some of the parameter we introduce in the reaction, the parameter is temperature, pressure, and concentration. By these three parameters, chemical equilibrium may be altered or changed. Chemical equilibrium change by using the three parameters: concentration, temperature, and product. So how we predict whether the equilibrium or direction of equilibrium change if we change out of three any one of the out of three parameters. First, we consider that the reaction in which A plus B particles converted into C plus D particles in the ratio of 2, 3, 4, 5, just for the random number for balancing purpose. They're all in the gas state. This once the reaction becomes at equilibrium, but we are not satisfied or we are trying to pursue the equilibrium may alter or changing the equilibrium direction. So for example, we add during the reaction, this is a closed container. After the reaction, or we thought that the reaction at the equilibrium, or we know the time at which the equilibrium is maintained, we put the sum or increase the sum amount of the or increase the sum concentration of it. First, equilibrium altered by the three parameter. First is called concentration. Second is called temperature parameter. And third is pressure. We may apply all three parameters simultaneously, but for the general understanding purpose, an examiner consider one by one parameter at a time, and remaining parameter will be constant. For example, we discuss first the change in concentration parameter. If we increase the concentration of A, whatever the concentration of A initially present, like 1.00 mole per dm cube concentration of A initially present, and we add few more particles like 0.5 moles of mole per dm cube particles of A also added in the reaction chamber by putting some gas syringe or any other apparatus, increase the concentration. Equilibrium shift towards the direction where the concentration is increased toward where the direction where the concentration of the particles is not increased. Means this statement is that if we increase the concentration of reactant, increasing concentration of reactant shifts equilibrium in forward direction or vice versa. If we increase the concentration of reactant, either of the reactant, the equilibrium shift toward the forward direction and more product will be formed. To maintain again the equilibrium point, like seesaw, if you just put some disbalancing, if you consider that this seesaw is initially on the balancing form, and you reactant and product particles on balancing form, and you put some reactant particle here to disturb the balance. So equilibrium is self-sustaining or self-maintaining process. So it generally produce more product to maintain the equilibrium again. Chemical equilibrium affected or stressed by the three parameters: concentration, temperature, and pressure. And how the parameter will be dealt for the concentration. If you increase the concentration of reactant, equilibrium move towards product side. If you increase the concentration of product, equilibrium move towards reactant side. Increase the concentration of reactant, shifts equilibrium in forward direction. If you increase the concentration of product, make the statement vice versa, in backward direction. Is one more addition of this statement is make the statement very interesting as well, which is that increase the concentration of reactant, increasing the concentration of reactant or decreasing the concentration of product, both have the same effect or same means. I said increasing the concentration of what? Concentration of reactant is equally balanced or equally as decreasing concentration of product. If you increase the concentration of reactant or decreasing the concentration, this is for the presentation, for the increase in concentration or decreasing the concentration of product. In both case, equilibrium towards the forward direction. Increasing concentration of reactant, increasing the concentration of reactant is same as decreasing the concentration of decreasing the concentration of product. Both have the same effect. Equilibrium shifts forward direction. Means more product will be formed. And you also make some vice versa statements. If you try to make a statement vice versa, increasing the concentration of product is same as decreasing the concentration of reactant. Means that equilibrium shift toward backward direction, more reactant. Increase the concentration of reactant by putting the some addition amount of the reactant. Decreasing the concentration of reactant, maybe the reactant particle can easily condense like ammonia, like sulfur dioxide, which sublime. So you can, it's a sulfur trioxide which can easily sublime or solidify. So you can easily put down to the solid state and is extracted from the reaction chamber. Whatsoever the process is not about the detailing of the process. It's just about how to the deal with the concentration effect. Increasing the concentration, equilibrium move to forward direction. Decreasing the concentration also have the same. Decreasing the concentration of product have the same effect. Or in other words, increasing the concentration of product or decreasing the concentration of reactant, both have the same effect. Means equilibrium shift towards backward direction, more reactant, less product at equilibrium time or equilibrium state. For temperature and pressure, we just hint and discuss in the next class in or more detail about the temperature and pressure effect. For temperature and pressure effect, you must first, for temperature effect, you must require to first classify your chemical reaction either as a delta H value negative sign or positive sign, which is called exo and endo. Exo for negative del H values, expel heat from the reaction chamber. And second term is called endothermic, which means the absorbed heat. For example, if this reaction is delta H values positive sign, means the reaction is endothermic. So endothermic reaction, and you try to increase the temperature. Your stress is temperature, and your temperature of the reaction mixture increase. So when the reaction temperature mixture increases and reaction is endothermic, equilibrium move forward direction. First have to remember this fact, and then we discuss in the detail by using the Legendre principles and other parameter logic basis. And second, if you decrease the temperature on same condition, equilibrium move in backward direction. It might possible some of the chemical reaction, like we just put the value negative sign here to understanding purpose. If the reaction is del H negative, means exothermic. So make this statement literally inverted. You are going to increase the temperature. We draw this one from the different color for understanding purpose. You increase the temperature of the reaction mixture where the del H values are in negative sign. Del H value negative sign means exothermic reaction. Means exothermic reaction. Increase in temperature. Here is the equilibrium in forward when endo. Here is the equilibrium is forward when endo. So means that just opposite to the endo is reaction move to the backward direction. And if you decrease the temperature for the same reaction, which is exothermic in nature, del H negative or exothermic reaction move in forward direction. Now, next time, inshallah, I will be discuss in more detail both effects with using Legendre principle as well as the pressure effect. Now is only from the, this is all about today class. Thank you.